And that brings us to the last talk in this session by Professor Tapas Maji, who is from Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore. And he's going to talk on metal organic self-assembled soft nanomaterial for solar fuel production.
Yeah. Okay. Thank you, Didi. At the outset, let me thanks Professor Tony Cheetham for inviting me, and also His Highness for the generous support in the SSL laboratory at JNCSR, and also the whole IWAM team for this wonderfully organized this symposium. Okay. So next 35 minutes, what I'm going to talk about, new type of material. New type of materials, that is the metal organic self-assembled soft nanomaterial for particularly solar fuel production. So yesterday we have heard a couple of very interesting talk, how this green hydrogen is so important, and particularly the CO2 reduction to some kind of the value-added product is what is the too much important in the current context of the energy and environment. So we know the different type of semiconductor-based photocatalyst, just a previous talk that oxide like the TiO2-based catalyst for that light harvesting. Then we have the organic-inorganic hybrid-based catalyst like metal organic framework, metal-free systems like the covalent organic frameworks. There are well-known semiconductor catalysts for this kind of solar fuel production. So in my talk, I will focus that soft material, how the intermediate states of the nanomaterial can be useful for catalytic applications. So what is the supramolecular polymer? The supramolecular polymers. So you have like this organic chromophores here. This organic chromophore through non-covalent interaction, pi-pi or hydrogen bonding interaction, they forms the one-dimensional polymer. And these one-dimensional polymers, when they're self-aggregates, they can the cross-link also. So why these supramolecular polymers has the controlled synthetic process? You can design these materials in the laboratory, these chromophoric molecules, which can be light harvesting, it can be the electron acceptor, it can be the electron donor, and you can conjugate it. And in between the characteristics, it will be the homogeneous and heterogeneous system. And if you have the nanomaterials, that will be the higher surface area, and which will be the efficient charge carrier mobility, and which is structurally and chemically tunable. So when such materials cross-link together, like this, sorry, I have. So when this such kind of one-dimensional fibril structures cross-links, they forms the gel. And this, when is the soft material gel, they have the highly processable, and this is the heterogeneous systems, and the adhesive surface for modulations with the co-catalyst, and it can mimic the enzymatic environment for catalysis. Okay. So how to design it? So you have to have some sort of the spacers like organic chromophores, which have the benzene, naphthalene, anthracene, pyrene, or many other organic chromophore. Then you can have the functional group you can attach with this, and this, then you can connect the metal ion, and eventually you can form the metallosupramolecular polymer. And these metallosupramolecular polymers can be the one-dimensional, and through the supramolecular interaction, they can further propagate and to get the higher order structures. And when you have these metal binding sites, so let's say you have the porphyrin core, which can connect with the nitrogen, that the binding constant K value is the 10 to the power 3 orders, but you have the bipyridine system that it can chelate, the increasing the donor atoms in the metal binding sites. You can have that binding state, it increasing to the 10 to the power 5, and you have the 3 binding donors, that chelate site, it can further increasing the binding site to the 10 to the power 8, 10 to the power 8 molar inverse. So in our design approach, so what we essentially design our such sort of material. So you have the pi chromophoric system. this pi-chromophoric system generally propagate the properties of the such kind of soft material. Let's say you have the naphthalene diamide, which is electron acceptor, or you have this azo, or you have this kind of steel beam molecules, or the pi-chromophoric systems. So this can to propagate the properties, then you connect it through the alkyl amide chain, and it is connected to the terpyridine linker, which is the metal binding site. So this will go to your pi core, and it can propagate through the pi-pi interaction. Then this binding or functional group, it will give the hydrogen bonding interaction, and then you connect with the metal binding site. So it can the one-dimensional structures. Okay. So now it can be the bipodal, or it can be the tripodal, or you can have the building block with the tetrapodal things. And based on these things, this kind of soft supramolecular network you can form, and these supramolecular one-dimensional polymers then can cross-links, and you can get the three-dimensional architectures for this kind of gel formation. So what we have designed, so now if you put the metal ion there, sorry. So if you put the metal ion here, so metal ion can give into the systems. There are the redox properties, optical properties, and electronic properties of the metal ion. You can introduce such systems, and you can tune the nanomorphology by binding of the metal ion, and the high processability of the soft material can be useful, particularly the different application. It can be stimuli responsive, self-healing, sensing, gas storage, catalysis, and drug delivery. So many other things you can do based on the synergistic application of your low molecular regulator and the metal ion. So in our approach, if you have the supramolecular catalysis, you can want to that green hydrogen production. So what it can do, you have now the core, you can use the light harvesting moiety, and you have the covalently attached metal ion, which can act as the co-catalyst, or you can further introduce another co-catalyst which can act as the catalyst for either the green hydrogen production or the CO2 reduction. So you have this advantage of this. So when you such kind of soft material, you can put in the solvent, which will give that higher order dispersions, efficient diffusion of the charge carrier, you have the structural tunability, and you have the large surface area. So as I told that you have the core, which is the pi-chromophoric linker, which can act the light harvesting moiety to the metal ion, but the reverse electron transfer, if sometimes the metal complex can also act as the light harvesting moiety, and your core can also act to the catalytic site. So as you know, this is why you need the catalyst. So you have this, let's say, CO2 plus waters. This is your free energy. But this activation energy is very high, and catalyst can decrease the activation energy to efficiently proceed this reaction pathway to form your different kind of the product. So in semiconductor catalyst, you have the different type of, let's say you have particularly the few things you have to careful. Now you have the absorb the light, and this can create the electron and hole. So now this catalytic process, this these electrons can reduce particularly in case of the CO2, you have the proton and the electron couple reduction, you can get the different product based on their different reduction potential. So now in this efficiency of the catalytic, you have the three things, particularly you have to look that it can absorb the visible light. And these electrons, the electron in the excited states would have the higher lifetime, and then it can go to the catalytic side, do the catalytic activity. So I want to bring your notice here. Let's say CO2, when it forms the 2-electron reduction or 2-electron 2-proton reduction, it can forms the CO. And you can see the reduction potential in this NH is minus 0.53. But if you look at the CH4, the reduction potential is minus 0.24. Which is thermodynamically more facile process. But if you look, the number of electrons is the 8-proton, 8-electron process. This means you have to have the kinetics of the electron transfer, it has to be much higher in this process. So that is some of the challenges of this CO2 reduction reaction. This is, you have the high energy requirement to break the CO2 molecules. The CO bond energy is 750 kilojoule per mole. Secondly is the pore solubility of CO2 in aqueous medium. And you have the, as I told you, 8 proton reduction for CH port. So the kinetic aspect is also very important. And you have to maintain the stable catalytic proportion over the extended period. Means your catalyst should have to be very stable. So over the years, what we understood that how the catalytic efficiency and the product, it can change the course of the reaction. So it should have your catalyst, it should have the visible light harvesting properties, and it should efficiently create charge separation, which can increase the efficiency. The band gap, homolomo redox equivalent of the catalyst, which can tune the product selectivity. Available CO2 binding site in the catalyst. And also, let's say you have the single atom dispersion of the catalytic site over the whole matrix. Coordination environment, the redox nature of the metallic site, the role of sacrificial electron donor, presence of the co-catalyst and solvent system, and formation of the donor acceptor diode for the better charge separation. So these are the few things which we need to look at, and I will, in my talk, I'll able to tell you some of this example where particularly the role of sacrificial electron donor or some of this, the redox nature of the metallic site that plays the significant role for that your product selectivity and product tunability. So this is the first paper by Samuel Stoop group, which really asked our group to think differently. This is the perilene chromophore, okay? So this is the perilene. It is connecting to this kind of the amphiphile kind of molecules. It is that you have the hydrophilic head, and this is the pi chromophore. So when it self-assembles, it forms the supramolecular polymer, and eventually the crosslinks, it forms to the gel, okay? So this acts at the light harvesting moiety. So what they told that when it is connected to this, the exciton migrant is very, very efficient. The faster transport of the exciton to the catalytic site. What catalytic site they have used here? So they used this nickel. So they co-localized into the gel matrix this catalyst, non-covalently. So what when they done the water splitting reaction for the hydrogen production, they found that in the powder state, the efficiency is quite low. The turnover number is very, very less. But when the catalytic activity in the gel phase, this is the hydrogel, you can see the turnover number significantly enhanced. So this thinks that when you have this kind of the particular nanostructures, your exciton separation or exciton migration is the faster. It localizes the catalyst in the chromophore using the gel phase much efficiently, and the diffusion of the proton to the solvent will be the much faster because you are using this same solvent system. So but the one problem is that in this case, because they have used the nickel complex as the catalyst, and it is not covalently attached to this kind of the chromophore. So eventually, when they term the number of cycles, the catalytic activity slowly decreases because it's come out from the solvent system. To address this thing, so we feel that it should be the covalently attached, and we can take the help of this nature. Okay. So if you look at the chloroplast structures, so you have now in the thylakoid membrane, so thylakoids, when that membranous sacs, it forms this one-dimensional kind of stacks, and this is called the grana. And if you look that in the thylakoid, little bit more details of this membrane structure, it is well known in the photosynthetic systems, the different type of this proteins and other redox equivalent, they are co-localized in the supramolecular self-assembled systems, and the nature does it very, very efficient way. But although this is not that the efficient process, whatever nature is done. So we thought like the same way, the different in the solvated and in the co-assembled systems, you have the light harvesting moiety, you have the catalytic site or the co-catalyst in the solvated macromolecular assembly. It can create the microenvironment, and it can source the efficient catalytic activity based on the substrate diffusion, electron migrations, and other way. So now come to the first part of my talk, that first the visible light-driven multi-electron photocatalytic reduction of CO2 using the coordination-driven metal-organic soft material, which is done by the Parul. So in our design, that we have taken the nature which has taken the porphyrin core. So porphyrin is well known that you have the light harvesting moiety, and it can the panchromatic absorption because it can absorb the whole visible light of the solar system. And it can also promote the light-induced different electron transfer process. You have this porphyrin, and this energetically different low-lying states it can process. So in our design, now we have the porphyrin core, then we frame the tetracarboxylate molecules, and through the alkyl amide chain, we connected this 4-terpyridine module, which can bind the metal site, and this metal site can be covalently attached and form the 3-dimensional higher order architectures, where that electron transfer, it can happen from the porphyrin core to the metal sites. So after the synthesis of this material, we have done the absorption. You can see this is the first, you have the solid band at 400, and there are 4 Q bands. And when you excite at 400, it gives that emission around 600 nanometers. Because of this, you have the solid band. So these are your LUMO plus 1, it comes from the solid band, and you have the 4 Q band from this HOMO to the first LUMO, and there are different symmetry, and it gives the 4 Q bands. So because of the solubility natures, we are able to form the gel in the DMSO media, and the rheology studies suggested that this is the viscoelastic material, where the G prime is higher, storage modulus is higher than the loss modulus. And when you see the absorption spectra, that you can see that it is almost the whole visible light, there is a absorption, because it is now in the aggregated state through the pi-pi interaction. And this is that your TM suggests this is kind of 2-dimensional sheet-like structures. And you can high resolution. This is the porphyrin codes through the aggregated through the pi-pi stacking. So then we have integrated that it is the well-known studied molecules ruthenium, because you know the ruthenium, it shows very interesting MLCT transition in the visible light around 450. And now when you connect this one that we have done, how the binding strength did this, when we have performed the titration study, this is the new band is appearing. And you can see the binding constant is around 4.5 into 10 to the power 4, you can get from the Benesi-Hildebrandt plot. So then with the presence of the ruthenium, we have make the gel, and you can see that drastically it changes the morphology. It was like seed kind of structure in the organogel without ruthenium, but it changed to that you have this kind of the nanoscroll lipomorphology, which it's changed under the rheology properties that the G prime, that it significantly enhanced compared to that your organogel. So the band gap almost remains same, and that how it is happening, this kind of the metal coordination. So this metal coordination and the ruthenium, it forms like that you have the orthogonal binding. Okay, so it will not bind in the phase-phase manner, rather it will bind in the orthogonal fashion. That's why it's the dramatically change the morphology from your 2-dimensional to that kind of, you have the nanoscroll kind of morphology. So then through that Matsotki analysis and through the DFT calculation, we have created the band diagram. And you can see this, particularly the conduction band position is the minus 0.7. So this material can eventually reduce CO2 to CO or CO2 to CH4 or many other, even CH3 to CH3OH and other things, because it's the LUMO position is the redox equivalent is much higher. So then first we have done this photocatalytic activity in the laboratory condition, and we have taken this condition 1 milligram of catalyst in acetonitrile medium, and we have taken this 2 ml of triethylamyl. So you can see it produced significant amount of the carbon monoxide. It's produced 41.9 millimole per gram with the selectivity around 99%. And this the rate of 3.5 millimole per gram per hour. So turnover number is quite significant in the 92.7, and quantum is 3.7%, and at the 450 nanometer, that is your solid band. So we also, what is in presence of the triethylamine, and we eventually from the LCMS study, we have seen that first it is the triethylamine, it goes to the diethylamine plus acetaldehyde. So this is the catalytic recyclability, and So you have this, the multiple cycle we have done, and it is equally stable. So this laboratory condition then we have done in the rooftop, in the sunlight condition, and this catalytic activity is equally stable, means that it forms the same amount of the rate of the reaction. Also, we can able to do only the 6 hours during the sunlight, and of course, it is the weather dependent. So then, another the interesting aspect of this work, so we changed that triethylamine to that sacrificial electron donor through the BNAC. Okay, so it is 1-benzyl 1,4-dihydronicotinamide. So this, when it gives the 1 electrons, this forms the BNAH radical cation, and through the proton abstracted from the triethylamine, it forms BNE, eventually it's dimerized. If you look at the oxidation potential for the triethylamine, it is the 0.69 volt. But in case of the BNAH, it is 0.57, so the reductive power of this kind of molecule is much more, and where we have dimerized, it is further decreases to the 0.267. So this can be reductive quenching of this material, it will be much more easy. So then we perform the catalysis with the, in presence of the BNAH, and the product selectivity drastically change. Earlier, in presence of the triethylamine, we have got the CO, but when you use the BNAH, this amount, it's produced the CH4 with a significant amount, 94.12 millimole per gram with the 95% selectivity. And this, the rate is 6.7 millimole per gram, and turnover number is quite significant, 208.3 in 14 hours, and quantum yield is 7.6%. So from this, the 2 electron reduction process, you are getting that 8 electron reduction process in presence of, by changing the sacrificial electron donor. And these formations of this, the dimeric species, we have monitored from the LCMS study. So this is quite significant that by changing this sacrificial electron donor from this 2 electron reduction process, you can change to that 8 electron reduction process to CH4. So this then, to understand this, so we have done why it is happening. So first we have done the transient absorption study. So this first, that molecules, we have 400 nanometer plus laser we have excited. So this is the excited state absorption of this gel. And you can see there is the positive absorption. And then we feed that the dynamics of the data. So then there is a two-way. You can, the relaxation process, there is a, from the first relaxation process, it skips for the particularly organogel, T1 is the 255 picoseconds. But when you have the coordination in presence of the ruthenium, the first component, that T1, it is very, very fast, okay, that 40 picoseconds. This means that the electron migration is happening from this, the porphyrin systems to that you have the ruthenium system. So that's the first electron transfer is helping for this catalysis. So when you have done the physical mixtures of this ruthenium tarperidine and the low molecular regulator, your T1 is 300 picosecond. So that indicates that is not the facile process compared to when you have the covalently connected the ruthenium tarperidine through the alkyl amide chain. So then to further understand this, we have performed the operando study. This is the drift study. So you can see when you have the after 30 minutes of the irradiation, first you have the background without CO2, only this, the catalyst. Then you, with presence of the CO2, you irradiate the light. This is the Mantis chamber. And you can see with the time that first you can get the carbonate, bicarbonate, monodentate carbonate. And now you can get the COH, that is the intermediate state, 2 electron reduction process. This increases with the time, and you can get the CO at 2080. So further, we have done the free energy calculation of this process. To understand catalytic size, first this absorbs the light and electron and hole, it separates. These electrons, and this goes to the tarperidine site, and this tarperidine, the second electrons, when it's bind, there is the exorgic process here, and then it's goes to the second electron, ruthenium 2 become the ruthenium 1, and eventually then bind to the CO2, and 1 electron, 1 proton transfer during the COH, and this removing of the watch H2O, gives the CO. So all the process is exergonic process. So then in presence of the BNAH, we have also done the operandi study that you can see we can track the other intermediate also. that instead of the CO intensity is very, very small here, rather you can getting the CHO, CH2O, CH3O, others intermediate, you can get it from there. And eventually that you can getting that CH2 stretching frequency. That means it is that from slowly, this process as after in presence of, because if you can see this process in presence of the binage is the delta zero value is much lower compared to. So this process goes to the 8 electron reduction process, and from this free energy diagram which is much more profile. Okay, so this what we have able to do by changing this of your the light harvesting process by changing your this so electron donor, particularly the triethylamine of the binage, you can change, retune the product and the product selectivity from 2 electron reduction to that 8 electron reduction process. Okay. So then we thought, okay, you can do that if you connect here some kind of metal which can act the catalytic side. So we can have just recent, we are trying to starting this work. So if we put the cobalt and then we put it, as in the previous work, we have the ruthenium here. Ruthenium, this terpyridine, it is the also well known the light harvesting moiety. So whether we can see the reverse electron transfer from this to this. So here we have now that MLCT, and this from the theoretical calculation, it is suggesting that LUMO, when the cobalt is connected, is lower from this, the LUMO from the ruthenium terpyridine. And then, so what? Making this. It's not slide changing. Got stuck. Yes, it is not going back. Yeah, very pressed. Yeah. So in this case, that when we connected, that you can see that MLCT band, and this is from this other characterizations we have done. So this is the photocurrent and this impedance measurement. So when you have the cobalt, that you can see the charge transfer resistance much more lower. And you have this from the photocurrent, it is very fast, the facile electron transfer it is showing. So now, to our surprise, here the CO2 reduction products is that again that 8 electron reduction product, and C2 product we got CH3 acetic acid from here, from ruthenium, and eventually that electron transfer from this ruthenium to these things is happened. So it is the reverse electron transfer, you can get it. Okay. So now the same systems, you can co-localize that one molecules that for this you can have the for photocatalytic hydrogen production. So when we done that ruthenium CPG, that the hydrogen productions we got in the synthesized CPG is around 63.8 millimole per gram, and activity is 5.6 millimole per gram per hour with this quantum efficiency of around 8%. Okay. But OG is not active without metal ion. So, and again, we have done under the sunlight and different control experiments we have done. Let's say that we have the ruthenium, porphyridine, ruthenium, just that it is much more active in presence of the ACD is the triethylamine. And it is also equally active in the sunlight medium. So, direct. So then we have prepared that simple molecules which mimic the dihydrogenase enzyme, di-iron cluster. It is the iron is the +1 oxidation state. So then during the gelation, we have co-localized it, and this co-localized, and it shows that you have the similar kind of the morphology, which is that previously called the ruthenium CPG, and different characteristics we have found. This is the 1.8% of the presence of these iron clusters in this. So when we have done this photocatalysis of this material, that it significantly improved. That you have, so earlier case, it was the 56, now it is becoming double with the 126 millimole per gram, and with the activity of 10.62 millimole per gram per hour, with the turnover number is significantly high when you have connected to this diiron cluster. Okay. So this is also highly stable, and we have also recovered the catalyst, and we also perform under the sunlight, and it is showing the significant activity as in the laboratory condition. So then we understood from the theoretical study that from the LUMO positions of the ruthenium from this porphyrin core to the LUMO of the ruthenium terpyridine, then you have the LUMO of the diiron cluster. So there's a cascade electron transfer process, and which is also supported by the transient absorption spectra. So this, when you have the Fe2CpG, that your first, which is the singlet type of quenching happened from the porphyrin, it is become from this 40 picoseconds, here it is now 1.2 picosecond. Okay. So yesterday, Didi has given very beautiful talk about that exciton separation or exciton separation. And for this, we have designed again. This is the tetrathiophulvalin ligand. It is the electron donor. And again, you have the four connected, you have this metal binding site with the terpyridine you can connect. To understand that whether the redox active ruthenium or the redox active any molecules has the role, here we have taken the zinc site. Okay. Zinc is the D10 electronic configuration. In a previous case, ruthenium can become the ruthenium-1, and which is the significant impact for during the catalysis, because it can directly accept the electron, photogenerated electron. But when you have this zinc, D10 electronic configuration, it is the redox inactive. So in this case, what we observed that this, again, it forms this fibrous structure, which I'm not going to do the details, similar kind of characterization. So and this is the form that your CT interaction from the terpyridine to donor acceptor interaction. So there is the electronic push-pull effect. So electron or that exciton separation, it will be much more faster. And we have done many different calculations to understand this thing. So now, if you look at the catalytic activity, so when you have taken just this zinc terpyridine with the TTA, that is not so high. It is the 530, the rate is around 530 micromole per gram, and CO2 to CO production is also not significant compared to the previous result. But when you add the platinum little bit of this, so there is an enormous rate increasing from this 14.72 millimole per gram per hour, and CH4 is around 290 micromole per gram per hour, and selectivity is the 97%. So what is that we try to understand about from this work? So this means you have to connect the metal ion, which is the redox active natures. Okay. Otherwise, this electron migration can happen, or you have to add the co-catalyst. Earlier, this because the D10 electronic configuration that cannot, it can bind the metal ion supports, but through this electron, it cannot accept the metal ion, so the catalytic efficiency is decreased. But when you add the platinum, it significantly enhances. So I have another 2 minutes. Okay. 2 to 3 minutes, I just tell you that earlier, during the gelation, as I told you, the metals played the significant role. But now, if you have the metals, and there's some sort of building block, and you have the extra organic molecules, and you can connect with this kind of metal qubits, forms that interesting nanostructures and the different properties. So for this is the one metal organic cubes it forms. And it's the dimethylamine cation that yesterday Didier was telling that cation in the perovskite structures. So this, through the hydrogen bonding interaction, so this is the discrete cube you have, and it has the negative charge, okay? So this MOC, it is connected with this dimethyl cation through the charge-assisted hydrogen bonding interaction and forms the three-dimensional structure. So now, when you dissolve these things in the water, it forms the clear solution, like you are dissolving a metal salt here. Okay? So then when you do the HRMS, we found the MOC is stable, and this overall surface charge from the zeta potential is minus 33 millivolt. And when you add that into the binding this aqueous solution, it forms the hydrogel, okay, the transparent hydrogel with this MOC through this propagation through the charge-assisted hydrogen bonding interaction. So then, through the rheology measurement and corresponding the FECM and TM suggesting this is the beautiful nano-tubular morphology, and this is the aerogel, that is your three-dimensional architectures remain intact, and this is the micron size, and you have the diameters of around 80 to 100 nanometers, and the thickness is 9 to 15 nanometers. So around 7 to 8 gallium MOCs are assembled, and it is assembled through this. To understand this, we have done the time-dependent study. Okay. So first, in the 2 hours of the gelation process, it forms like the flakes, and each flakes at the nodal point and after this 4 hours, it forms the anisotropic growth of the nanotube. And after 6 hours times, it can the partially forms tube, and eventually at the 8 hours of times, it forms that beautiful, perfectly aligned this nanotube. So what we can do this nanotube? So when we measure the zeta potential of this nanotube, we understand this is negatively charged, and then this negatively charged, it can absorb the cationic dye, and it can reject the anionic dye, and it can partially have the deuterionic dye. And this gel is the pH dependent. The original pH is 11, and if you change few drop, if you give the few drop of HCl, it's the pH become 4, and it's becoming the salt, and eventually that you can, few drops of ammonia, it can form. So then we try to make the gel chromatographic separation using this gel. So first, what we have done, we have taken in this tube the gel, and we have taken this Nile blue and sulforodamine G. The Nile blue is the positively charged dye because it will give the better visual demonstration, and the sulforodamine G. But you can see this slowly, that the sulforodamine G, based on the electrostatic repulsion, it can go out from the gel, and slowly that your absorbance increases, then the Nile blue go out here. And if you change the pH of the medium, so eventually just you can get it out this, again, this Nile blue from the system. So you can separate the two molecules, positively or negatively charged molecules, and you can extend to the different type of system. So we have done that binder you can change to get 1 minute. So binder you can change, and it can give the different type of nanomorphology. So particularly the diethylamine, and you have the beta-alanine, and so on. So these things then we have further added, particularly this donor acceptor, then you can modulate, and you can get the white light emission, which I'm not going to the details. So what is the next things you can do using this? Just one slide. You can take the simple molecules, like the copper ethylene diamine, and you can make the supramolecular polymers. But inorganic medium, this inorganic complex like supramolecular and corresponding gelations, it is not study, and you can get that this putting the redox active molecules, you can do the electrocatalysis and other one. Not only that, you can put the bicomponent systems, like the iron, it can form the gel, and iridium, it can form the gel, and eventually that when you can mix together, it can get the beautiful, this tri-component gel you can get. And because there is the organizations of this iridium and the iron, it can beautifully organize in the three-dimensional structure, and you can study the photocatalytic activity, and which I performed, and we got the CO production here, okay, and which you'll track. So last, that what have I told, that the soft material can be eventually used for the photocatalytic applications, where the covalent integrations of that your light harvesting moiety and the catalytic sites keeps that very important, because the electron transfer pathway will be shorter and it will be faster, and you can tune the product by changing that your sacrificial agent. Also, you can change the metal ion from this ruthenium to zinc to modulate the properties, and you can biomimetic approach to, you can get the green hydrogen production, or such kind of the discrete metal organic cube, you can multi-component gel you can produce for the light harvesting application or photocatalytic application. And finally, I want to acknowledge my group. They're a bunch of highly dedicated students. They work really hard. And so financial support I get from the JNC, CSR, Government of India, SSL Research Facility, and this, we have the supercomputing system, and from this, sometimes to understand the geometry of this in the metal line, we use the beam line, particularly X-ups measurement, and we should happily collaborate that this is the work. And also, thank you for your kind attention.
Just time for very short, brief questions, a couple of them at most.
Okay.
Okay. Yeah, we have to start. I know, we started 8 minutes late, so we really are running out of time.
But we've got to keep it on time.
Okay, so I think we'll allow the tea coffee session to